Hey everybody, welcome to video number 4 on that most beautiful of all mathematical subjects, complex numbers and complex analysis. In video number 1, we looked at powers of the imaginary unit I and saw some pretty interesting things. In video number 2, we moved on to visualizing complex numbers, both as points and as vectors. And in video number 3, we talked about adding complex numbers and how to visualize that both in terms of vector addition and translational transformations. In video number 5, I want to talk about complex number subtraction, but before we do that, I thought it would be a good idea to talk about scalar multiplication times a complex number. What does that mean? It means a real number times a complex number. If we think of complex numbers as vectors, it's going to rescale them, and if the real number is a negative real number, it's also going to reflect them across the origin. As always, we emphasize exploration, discovery, and joy in discovery. And if you like this content, please like, comment, share, and subscribe. It really helps the channel out. Let's start by considering, well, what seems to be one of my favorite complex numbers, z equals 4 plus 3i, and ask what it would mean to multiply this complex number by a real number. For example, the real number 2. What should it mean to multiply this by 2? 2 times 4 plus 3i. If you had to guess, what would you do? What would you guess? I hope your gut instinct would be to distribute the 2 through the parentheses. If indeed you thought of 4 plus 3i as being, say, a linear polynomial in I, ignoring the fact that I squared is -1, that would be what you would do with polynomials. So you get 2 times 4 is 8, plus 2 times 3i should be evidently 6i, since 2 times 3 is 6. The real part of the answer is 8, and the imaginary part of the answer is 6. How about if we multiplied z by 3? 3 times z is 3 times 4 plus 3i. Once again, do what we just did before. Distribute the 3 through. 3 times 4 is 12. 3 times 3 is 9. The answer is 12 plus 9i. The real part of the answer is 12, and the imaginary part of the answer is 9. Can we do this with fractions, for example? Could I multiply z by 3 halves? Certainly. 3 halves times z is 3 halves times the quantity 4 plus 3i. 3 halves times 4 is going to be 6. 3 halves times 3 is going to be 9 halves. The answer is going to be 6 plus 9 halves I. How about an irrational number like pi? Can that be done? Well, it's a little bit weird, but it certainly can be done. There's nothing stopping you from doing this. The answer is going to be 4 pi plus 3 pi I. How about a negative number? The most common negative number to use here is -1. What's -1 times z? Multiply the real and imaginary parts by -1. -1 times 4 is -4. -1 times 3 is -3. I could write plus -3i here, but it's more natural to just write -3i, and that is fine to do. I should remark that we can also write this as just -z, and ultimately this quantity is going to be what's called the additive inverse of z. When you add z to this quantity, you are going to get the number 0, which is called the additive identity. I could also multiply by, say, -2. -2 times z is -2 times 4 plus 3i is -8 minus 6i. Let's write down a general formula now. I'm often going to use the Greek letter lambda as my symbol for an arbitrary real number. This is an arbitrary real number. It's going to get multiplied by my complex number z, which is this particular complex number, 4 plus 3i. So the pattern is lambda times 4 plus 3i is going to give us 4 lambda for the real part and 3 lambda for the imaginary part. Being the imaginary part, it is still a real number, but it's next to the I. We are going to plot these points in the complex plane. I'm going to use graph paper here in a minute, but before we do so, I want to make a basic plot of 4 plus 3i and also introduce another important quantity called the modulus of a complex number, also known as the absolute value of the complex number, that is going to be an important quantity for us. So the complex number z equals 4 plus 3i, go 4 units along the real axis to the right and 3 units along the imaginary axis upward. 4 plus 3i is going to be right here. The modulus or absolute value of this complex number z equals 4 plus 3i is its distance to the origin. That distance right there. This does correspond to the absolute value of a real number. If you had a real number along the real axis, the absolute value of a real number, such as, for example, -5, is its distance to the origin, which would be +5. So that distance is going to be the absolute value of z. You can use the Pythagorean theorem to figure out what it should be. You've got a right triangle here. This side has a length of 4, this side has a length of 3. That distance right there by the Pythagorean theorem is going to be the square root of 4 squared plus 3 squared. That's the square root of 16 plus 9, which is the square root of 25, which is 5, a nice number. 25 is a perfect square. That's why I like z equals 4 plus 3i. Because of that, that is its distance to the origin, and we write that the absolute value of z, but again, it's also called the modulus of z, is 5 in this case. That's its distance to the origin. In general, if z has a real part x and imaginary part y, so that z is x plus iy, or z is x plus yi, I could also write, the modulus of z, its absolute value, by the Pythagorean theorem, is the square root of x squared plus y squared. Notice there's no I in here, okay? I'm thinking purely in terms of an ordinary kind of plane when I draw the complex plane. I'm thinking of the points as being complex numbers, but I can remember, think about this in terms of real coordinates. This corresponds to the point with real coordinates 4, 3. I can think of in terms of the ordinary Pythagorean theorem. In this formula, there are no i's. This is a real quantity, and in fact, it's greater than or equal to 0, no matter what x and y are. A general formula that I can write down based on the pattern that we see here for multiplying a real number lambda times z can be found as follows. What is the modulus or absolute value of lambda times z? It would be the modulus of lambda x plus I lambda y. By the pattern of this formula, that's going to be the square root of lambda x quantity squared plus lambda y quantity squared. Again, no I in there. That's going to be the square root, using properties of exponents, of lambda squared x squared plus lambda squared y squared. That expression inside that square root has a common factor of lambda squared that can be factored out like this. And it is a property of real square roots here that you can separate this into this product, the square root of lambda squared times the square root of x squared plus y squared. This thing right there is the modulus of the complex number z. What's this? Is that lambda? Well, careful. Lambda could be negative. This is actually the absolute value of lambda, or you could even call it the modulus of lambda. So what we've done here is we've derived a general formula that the modulus of lambda times z is the modulus of lambda times the modulus of z. We have verified this in the case where lambda is a real number. Though this turns out to be true, we'll see eventually, even when lambda is a complex number. By using graph paper, we can draw things here a little bit more carefully and see the rescaling property pretty nicely. Let me draw in red the initial vector, z equals 4 plus 3i. As a point, it's right there. The modulus of z is the distance of that point to the origin, but we can also think of it as the length of the vector for that point. So there is z. That is 4 plus 3i. Where is 2z, both as a point and as a vector? 2z was 8 plus 6i. Go to the point with coordinates 8, 6. Here's 8. There's up to 6. That's going to be right there. That's 2z. As a point, it's along the same length of the origin, but twice as far away, illustrating that property that we just verified. As a vector, an arrow, if we draw an arrow from the origin to that point, it is in the same direction as the original vector, but twice as long. Okay? And if we drew 3z, it would be in the same direction as the original vector, but 3 times as long. If we drew 3 halves, or 1.5z, it would be in the same direction as the original vector, but 1.5 times as long. How about negative z? Negative z, remember, was negative 4 minus 3i. Go to the point with coordinates negative 4 and negative 3 right there. As a point, negative z is right here. It's the reflection of this red point here at z across the origin. In terms of an arrow, here's its position vector right here. It's parallel to the red vector, but in the opposite direction. It does have the same length or modulus that z does. which shouldn't be surprising because the absolute value of -1 is +1. And we can make lots of other pictures for other scalar multiples of z. They're all along the same line in the complex plane. When we allow lambda to be a complex scalar, then rotations are going to come into play. At the moment, this just involves what you might call dilations, stretches, shrinkages if your scalar is less than 1 in absolute value, and also reflections across the origin. We could think of this in terms of a transformation. We could think of w equals f of z as being lambda times z, where lambda is a real scalar, as giving us another kind of function, a complex function of a complex variable that we could think of in terms of mapping properties. And we'll wrap up the video as usual by using Mathematica to illustrate these things, both in terms of rescaling vectors and also in terms of transformations, in this case dilations that can be expansions, contractions, and reflections. This code that you see right here generates a picture of vectors. We've got our scalar lambda that is initially set to be 1. The initial vector is supposed to be in red here. It's a little thicker than the blue vector, which is going to be the rescaled version of z. I can change the value of lambda. I can make it bigger, and I get a rescaled version of z going up. You can see the scalar in front of z. I can also make lambda between 0 and 1, and I get a scaled down version of z. I can make lambda negative, and the arrow points in the other direction. When lambda is -1, then it's the same length as the original vector, but lambda can be further away from 0 than -1 is, and it gets longer. The next bit of code thinks about transformations, dilational transformation you could call it, that involves an expansion, contraction, or reflection depending on the magnitude of lambda. Here we've got, like in the last video, some random points. We're going to look at images of these sets of points under the transformation w equals f of z equals lambda times z for different values of lambda. For example, if lambda is bigger than 1, like 2 for example, then these points are the images of the original set of points under the transformation w equals f of z equals 2 times z. It is an expansion, you might say, away from the origin. If lambda is between 0 and 1, it's a contraction toward the origin. And if lambda is negative, you get a reflection across the origin, as well as possibly an expansion or contraction, depending on the value of lambda. If lambda is less than -1, it's an expansion. If lambda is between -1 and 0, then it's some sort of contraction. You can see the points getting contracted. As always, strength and honor to you. Be strong. Also be an honorable person. We'll see you in the next video.